Hello, friends. Today, I invite you to join me on the greatest engineering adventure in human history. We're embarking on an incredible journey that starts with a tree trunk and leads to massive steel fortresses that traverse the oceans, nuclear submarines, and the autonomous ships of the future. In this series, Xenotation Spot the Phoenicians' secret keel technology, Xenotation Spot the Vikings' dragon ships, Xenotation Spot Venice's massive shipyard factories, Xenotation Spot and all the turning points that have changed the seas, from the Titanic to modern aircraft carriers. Loudspeaker for more content. Don't forget to subscribe to my channel, turn on notifications, and like the video at. With your support, we'll embark on many more historical journeys. Anchor. If you're ready, we're setting sail. The greatest revolution in human history, long before the invention of the wheel, was the ability to stay afloat on water. The story of maritime transportation may have begun with a person clinging to a log carried by a river's current. However, this coincidence soon sparked the first sparks of engineering genius. The most primitive but effective tools of ancient seafaring were rafts and hollowed-out canoes. Archaeological findings show that civilizations around the world, from Mesopotamia to the Amazon rainforest, used similar methods. Early humans created rafts by tying together light wood or bundles of reeds with plant fibers. Especially in Mesopotamia and Egypt, these rafts made from papyrus reeds were vital for river transportation. Papyrus's natural buoyancy allowed heavy loads to be transported along rivers. In parallel, monoxylons, or canoes made by hollowing out a single tree trunk, emerged. This was the purest form of shipbuilding. With the help of axes and fire, the interior of a massive tree trunk was hollowed out, while the exterior was sharpened to reduce water resistance. These canoes were used not only on rivers but also for fishing along the coast. The Pes canoe, found in the Netherlands and dated to around 800 BC, is the most concrete evidence of how far back this technology goes. So how did these simple tools evolve into structures that could brave the open seas? The first shipbuilders had to learn not only to stay afloat but also to master the water. Nature itself was their greatest ally in this process. Realizing the power of the wind and beginning to use simple pieces of leather or fabric hung on poles as a propulsive force opened the door to a new era in seafaring. For the first sailors, water was not an obstacle, but a vast road waiting to be explored. The small platforms placed on the first boats were actually the ancestors of the massive decks of the future. With these simple structures, humanity began to explore the world, trade, and carry cultures by following the coastlines. Maritime transport was preparing to become the main artery of civilization with these modest steps. The Nile River banks were the first place where maritime history truly institutionalized and transformed into an engineering discipline. For the Egyptians, the Nile was not just a source of water, but a massive highway connecting the country. As the current flowed northward, the prevailing winds blew southward. This natural phenomenon allowed the Egyptians to perfect the combination of sails and oars. By 3000 BC, the Egyptians were not only making reed boats, but also building real ships using cedar wood imported from Lebanon. However, Egyptian shipbuilding faced a very interesting challenge. There were not many long, straight trees suitable for building ship keels in Egypt. Therefore, Egyptian craftsmen developed an ingenious method called shell first. They joined short planks together using a tongue and groove method, assembling the ship like a jigsaw puzzle. The most iconic example of these ships is the massive structure known as the Solar Boat, located next to the Pyramid of Cheops. This ship, approximately 43 meters long, was built without a single nail, using only ropes made from plant fibers threaded through holes in the planks and tied together. When submerged in water, the ropes and wood swelled, making the hull completely watertight. This was one of the most sophisticated engineering achievements of the ancient world. The Egyptians began to make their presence felt not only on the river but also on the open seas. During the reign of Queen Hatshepsut, expeditions to the mysterious land of Punt proved that these ships could withstand the rough waters of the Red Sea. To strengthen the hulls for these sea voyages, massive tension ropes stretching from bow to stern were used. These ropes prevented the ends of the ship from sagging, giving the hull structural integrity. The square sails and wide or blades on Egyptian ships set the standard for Mediterranean seafaring for thousands of years. The pharaoh's ships carried gold, ivory, spices, and massive obelisks, shaping not only trade but also architecture and art. This first great experience on the Nile was the real revolution that enabled humanity to see the seas not as obstacles but as bridges. While the Egyptians specialized on the Nile, the Phoenicians living on the Lebanese coast turned their gaze to the open seas, beyond the horizon. They are considered history's first true seafaring nation. What set the Phoenicians apart from their rivals were their radical innovations in shipbuilding technology and their access to cedar forests. The Phoenicians made a revolutionary discovery in shipbuilding, the keel and rib system. Unlike the flat-bottomed ships of the Egyptians, the Phoenicians placed a strong keel running the entire length of the ship's center. This keel formed the skeleton of the ship and provided incredible resistance to the vertical pressure of the waves. Thanks to this structure, ships could be deeper, more stable, and faster. Now ships no longer just glided on the water, they cut through the waves. The Phoenicians had two main types of ships, round-hulled merchant ships called gallows, and long, slender warships. Merchant ships could carry enormous quantities of wine, olive oil, and their famous purple dye thanks to their wide bellies. These ships were designed to move solely by sail, which reduced the need for oarsmen and increased cargo space. Warships, on the other hand, required speed, therefore, they were equipped with numerous oarsmen and bronze-tipped rams used to sink enemy ships. The Phoenicians were also unrivaled in navigation. They were the first civilization to use the North Star for night navigation. In fact, the Greeks referred to this star as the Phoenician star for a long time. Unlike other sailors who were afraid to leave the coast, the Phoenicians crossed the Strait of Gibraltar and sailed into the Atlantic Ocean, bringing tin from England and gold from West Africa. Another of their masteries in shipbuilding was perfecting the caulking technique. They bound the planks together so tightly and precisely that the ships looked like a single piece of wood. This technique would remain the standard in the Mediterranean for centuries. By transforming shipbuilding from a craft into an industry, the Phoenicians became the true architects of the ancient world's global trade network. Ancient Greek seafaring, built upon the foundations laid by the Phoenicians, elevated shipbuilding to an art form and a level of high engineering. For the Greeks, the sea was both a source of livelihood and an impregnable fortress protecting the survival of their city-states. The greatest peak in shipbuilding during this period was reached with the emergence of warships called trireme, three-rowed. Triremes were the fastest and most maneuverable machines of the ancient world. These ships, approximately 37 meters long and 6 meters wide, got their name from the rowers seated in 3 tiers on each side. This massive engine, consisting of a total of 170 rowers, enabled the ship to reach speeds of 12 to 15 kilometers per hour. However, triremes were not only fast, they were also floating rams. Bronze-plated rams located just below the waterline at their bows were designed to smash the hulls of enemy ships. The material used in shipbuilding was usually pine, due to its lightness and flexibility. However, oak, which was harder, was preferred for the keel. Greek craftsmen used enormous tension ropes called hypozomata, which ran the entire length of the ship from bow to stern, to increase the ship's longitudinal strength. These ropes were a vital engineering solution that prevented the hull from flexing and breaking when the ship maneuvered at high speed or battled waves. An interesting feature of triremes was their very shallow draft. This allowed the ships to be easily beached for the night. However, this lightweight construction left the ship vulnerable to storms. Therefore, Greek sailors generally preferred to follow the coast rather than venture into the open sea. In terms of navigation, the Greeks began to integrate mathematics and astronomy into seafaring. The concept of the wind rose, which indicated the position of the sun, star charts, and wind directions, began to develop. At turning points such as the Battle of Salamis, the speed and maneuverability of triremes showed the world that even colossal powers like the Persian Empire could be defeated. Ancient Greece had gained dominance of the seas by combining aesthetics and functionality in shipbuilding. Rome was not initially a naval power. Rather, it was a land empire that relied on its legions. However, the Punic Wars with Carthage showed that Rome needed to dominate the seas to survive. The Romans' success in shipbuilding stemmed not so much from original inventions as from their ability to standardize existing technology and transform it into a massive industry. Legend has it that the Romans captured a stranded Carthaginian ship, dismantled it, and reverse-engineered their own fleet. By pre-numbering ship parts and establishing an assembly line, the Romans could build over 100 ships in just 2 months. This is one of the earliest examples of mass production in world history. The greatest innovation in Roman shipbuilding was the bridge called the corvus, crow. The Romans, who were inexperienced in naval warfare, would hurl this hook-shaped bridge onto enemy ships, locking the ships together and turning the naval battle into a land battle. Their superior infantry would then cross the bridge and easily capture the enemy ship. Although this heavy structure was eventually abandoned because it disrupted the ship's balance, it was this engineering ingenuity that secured Rome's first victories at sea. On the commercial front, the Romans built the ancient world's giant cargo ships. The corbetta ships, which carried grain from Egypt to Rome, had a cargo capacity of over 1,000 tons. In addition to the main mast, these ships used a small foresail called an armen that extended forward from the bow. This addition revolutionized navigation by making steering the ship incredibly easy. The Romans also developed a method of lead plating to protect the hull from marine life and decay. They extended the life of their ships by nailing thin lead sheets onto the wooden hull. In port construction, they used a type of concrete, puzzolana, that could set underwater to build massive breakwaters and shipyards that still stand today. Thanks to Rome, the Mediterranean Sea came under the absolute rule of a single power for the first and last time, becoming Mare Nostrum, or Our Sea. As the Roman Empire faltered in the Mediterranean, a completely different technology was emerging in the cold and turbulent waters of the north that would fundamentally change the history of seafaring, Viking ships. These ships were not merely a means of transportation, but the purest symbols of Scandinavian culture and engineering genius. What made Viking ships unique was that they were flexible enough to withstand the ocean's giant waves, yet shallow enough to navigate rivers. At the heart of Viking shipbuilding lay the clinker technique. Unlike the Mediterranean method of joining planks end to end, Viking craftsmen overlapped oak planks and fastened them with iron rivets. This method gave the hull incredible flexibility. As a Viking ship passed through the waves, it would bend like a snake, but it would never break. This flexibility in the hull allowed the ship to absorb the resistance of the water. The langskip, or longship, was the Viking war machine. The most distinctive feature of these ships was their symmetrical structure. That is, the bow and stern were identical. This allowed the ship to maneuver quickly by rowing in reverse without having to turn around in narrow fjords. The dragon head figures, drakkar, placed at the bow of the ship were carved not only to instill fear in the enemy but also for spiritual purposes, such as warding off sea monsters. The Vikings' navigational skills were far ahead of their time. In an era when the compass was not yet known, they could determine the position of the sun, even in cloudy weather using the sunstone, calcite crystal. They also succeeded in reaching Iceland, Greenland, and even the American continent, Vinland, centuries before Christopher Columbus by observing the movements of seabirds, the color of the water, and the migration routes of whales. For trade, they built larger, deeper-hulled ships called nar. Nar ships were designed to transport heavy cargo and animals over long distances. Viking ships, with their elegant lines and sturdy construction, were the most advanced seafaring vessels of the Middle Ages. Thanks to them, the Scandinavians carved their names into history not only as warriors but also as the world's most skilled explorers and shipbuilders. When the Roman Empire split in two, the maritime legacy continued to take shape in the hands of the Eastern Roman Empire, or Byzantium. The Byzantines developed the heavy triremes of antiquity into the most effective warships of the Middle Ages, known as dromons. Dromons meant running or fast, and these ships dominated the Mediterranean and Black Seas for centuries. The most significant structural difference of the dromons was that the ancient ram was replaced by a ram pole located above the water. This was used not so much to sink enemy ships as to break their oars and allow soldiers to board them. However, what truly made the dromons legendary were the bronze siphons placed at the bow of the ship. These siphons sprayed one of history's most mysterious and terrifying weapons, Greek fire, grijuva. Greek fire was a sticky, unquenchable liquid that continued to burn even on water. Byzantine shipbuilders had installed a complex pump and heating system inside the ship to launch this incendiary substance. This technology formed the Byzantines' absolute line of defense at sea. The approach of a dromon fleet meant inevitable fire and disaster for enemy fleets. An important transition also occurred in shipbuilding technology during this period. The hull-first construction technique was gradually abandoned, giving way to the modern method of first building the skeleton, ribs. This change allowed ships to be built larger, more durable, and more cheaply. Additionally, dromons began to widely use not only square sails but also triangular, lateen sails, which enhanced maneuverability. Byzantine shipyards, especially the Golden Horn in Istanbul, were among the most technologically advanced centers in the world. The double-deck dromons built here could carry over 200 rowers and soldiers. Soldiers on the upper deck fired arrows and stones, while rowers on the lower deck maintained the ship's speed. Dromons were as sturdy as castles and as fast as hunters. Thanks to these engineering marvels, Byzantium managed to maintain its presence at sea for 1,000 years. While Europe struggled through the dark waters of the Middle Ages, the art of shipbuilding in the Far East reached a completely different and revolutionary dimension. Chinese masters developed the legendary ships called junk, kunkka, whose design has remained virtually unchanged for centuries and has survived to this day. Junk ships were not just boats, but engineering marvels, with every part designed for functionality. The most distinctive feature of junks was their sails. Instead of fabric, they used straw sails supported by bamboo ribs. These ribs gave the sail a rigid structure and transmitted the power of the wind to the hull more efficiently. Furthermore, this system ensured that even if the sail tore anywhere, the whole structure remained intact. Thanks to this structure, which resembled modern shutter systems, even a single sailor could easily open and close the massive sails. However, the greatest legacy of Chinese shipbuilding to the world was in the internal structure of the hull, watertight compartments. Chinese engineers divided the interior of the ship into independent compartments using vertical panels. If the ship struck a rock and the hull was punctured, the water remained only in the affected compartment, preventing the rest of the ship from sinking. This safety system, which the Western world would only fully adopt in the 19th century, enabled Chinese sailors to safely cross the oceans thousands of years ago. In addition, they were the first to use the balancer rudder system. The massive rudder at the rear of the ship optimized water resistance through holes in its structure, enhancing the ship's maneuverability. The anchor systems used on these ships were also highly advanced. Made from a combination of stone and iron, these anchors could hold massive hulls steady even in the strongest currents. This technology reached its peak during the Song and Ming dynasties. Huge junks were used not only for trade but also as a show of diplomatic power. With their wide hulls, flat bottoms, and high sterns, these ships harnessed the monsoon winds and became the backbone of a vast trade network stretching from India to the shores of Africa. Chinese shipbuilders left an indelible mark on maritime history by combining the power of nature with technical ingenuity. By the early 15th century, during the Ming dynasty, China's shipbuilding technology had produced one of the largest wooden fleets in world history. At the heart of this fleet, led by Admiral Zheng He, were the baochuan, or treasure ships. These ships are considered the largest wooden structures ever built at that time. According to historical records, the largest treasure ships were approximately 120 meters long and 50 meters wide. This was more than 3 times the size of the largest ships used in Europe at the time. The sails of these 9-masted giants were so large that hundreds of sailors were needed to control them. The massive timber used in the construction of these ships was brought from special forests in southern China and assembled in huge shipyards. Treasure ships were not just vessels, they were floating cities. They housed diplomats, doctors, scientists, soldiers, and even areas of soil used to grow fresh vegetables. Watertight compartment technology was vital for such enormous dimensions. Maintaining the structural integrity of such a large hull was only possible with the support provided by the internal compartments. Additionally, heavy ballast weights were placed under the hull to increase the ship's stability. Zheng He's fleet could accommodate more than 300 ships and 27,000 personnel at a time. This fleet reached the coasts of Southeast Asia, India, the Arabian Peninsula, and East Africa. These massive ships inspired awe and fear in every port they visited. Chinese engineers also pioneered navigation by using compasses and star chart boards that measured the altitude of stars on these ships. However, when the Ming dynasty began to pursue a policy of isolationism, these massive shipyards were closed and the construction of treasure ships was halted. Had this technological advancement continued, the history of seafaring could have unfolded very differently. Nevertheless, Zheng He's treasure ships have secured their place in history as engineering marvels representing the pinnacle of wooden shipbuilding artistry. During the Middle Ages, sailors from the Islamic world were the absolute rulers of the trade routes between the Indian Ocean and the Mediterranean Sea. Arab and Muslim shipbuilders not only revolutionized transportation but also popularized one of the most important tools that would change the history of world maritime, the dhow ships and their characteristic Latin sail. Dhow ships were typically built on a sturdy keel called a dose. The most distinctive feature of these ships was that the hull sections were not nailed together but sewn with extremely strong ropes made from coconut fibers. Known as stitched ships, this technique allowed the ship to flex and not break if it collided with the ocean's harsh coral reefs or sand. This flexibility gave the ships incredible durability in the variable conditions of the Indian Ocean. However, the real revolution was in sail design. The square sails of antiquity only worked when the wind was behind the ship, but the triangular Latin sail allowed the ship to sail at an angle to the wind beam reach. This meant sailors could go wherever they wanted, regardless of the wind's direction. This technology would later inspire Europeans to develop their caravel ships and launch the Age of Discovery. The Islamic world was also experiencing a golden age in navigation. Instruments called the astrolabe and kamal enabled sailors to accurately measure latitude by observing the stars. Famous navigators such as Ibn Masud recorded the cycles of the monsoon winds with mathematical precision. This accumulated knowledge formed the maritime leg of the spice route, enabling goods from China to spread throughout the world via the Red Sea and the Persian Gulf. Muslim shipbuilders coated the hulls of their ships with a mixture of lime and whale oil to protect the wood, ensuring watertightness and protection from woodworm. The ships built during this period not only transported goods but also carried knowledge of astronomy, mathematics, and cartography across continents, laying the foundations for modern seafaring. By the 15th century, Europe's horizons could no longer be limited to the coastline. Portuguese and Spanish sailors needed a new type of ship that could brave the Atlantic Ocean's huge waves and unpredictable winds. This quest ultimately led to the birth of the caravel, which changed the history of seafaring forever. Unlike the heavy and cumbersome medieval ships used until then, the caravel was a perfect blend of speed, agility, and durability. Portuguese shipbuilders drew inspiration from both the Latin rig vessels of the Mediterranean and the sturdy-hulled ships of Northern Europe when designing the caravel. The caravel's most notable feature was its low draft and lightweight construction. This allowed them to navigate safely not only on the open seas but also in shallow river mouths and uncharted coastlines. The hull was no longer built using the Viking clinker technique but rather the carina method, where planks were laid side by side, resulting in a smoother and faster surface. The real power of caravels lay in their variable sail rigging. Initially using only triangular Latin sails, these ships were unrivaled in sailing against the wind. However, square sails were later added to capture the fierce winds in the middle of the ocean, leading to the development of the Caravella Redonda type. This hybrid system gave captains complete control in all weather conditions. These small giants, usually with 2 or 3 masts, were only 20 to 30 meters long, yet they had the power to connect the world. Christopher Columbus's famous ships, the Nina and the Pinta, were caravels. These ships were sturdy enough to withstand months of uncertain voyages, yet delicate enough to glide through the rivers of new continents. Caravels also featured a raised, stern castle at the stern. This structure provided shelter for the crew and prevented waves from flooding the ship. This technological leap in shipbuilding, combined with advances in cartography and navigation tools, opened the doors to the unknown world for humanity. The caravel was not just a wooden vessel with sails. It was a bridge that carried Europe beyond the ocean. These elegant ships, launched from Portuguese shipyards, made the first brushstrokes that defined the boundaries of the modern world. Although caravels pioneered exploration, the trade links established with newly discovered lands required greater cargo capacity. This need led to the birth of the carrack ships, the true giants of the 15th and 16th centuries. These ships, called nau by the Portuguese and nau by the Spanish, were a combination of the cumbersome trade ships of the Middle Ages and the high technology of the caravels. The most distinctive features that set the carracks apart from others were their enormous size and tall structure. The ship had multi-story, tall structures called castles at both the front, bow, and rear, stern. These castles not only transformed the ship into a floating fortress against enemy attacks, but also served as a shield, preventing huge waves from crashing over the deck in open seas. The carraca had 3 or 4 masts. It carried huge square sails on its main masts and a Latin sail on its mizzen rear mast for maneuvering. In terms of shipbuilding, the carraca represented the pinnacle of wooden ship engineering at the time. Their hulls were reinforced with very thick oak beams to carry thousands of tons of cargo and dozens of heavy cannons. Christopher Columbus' flagship Santa Maria and Magellan's ship Victoria, which circumnavigated the globe for the first time, were both carracas. These ships had enormous holds capable of storing the fresh water, food, and trade goods necessary for voyages lasting months. However, this size came at a cost. Carracks were very heavy and cumbersome vessels. Maneuvering them became quite difficult when the wind was not blowing from behind. Due to their tall structure, they were at risk of capsizing in severe storms. Nevertheless, they became the indispensable carriers on the main routes from Europe to India and America. With the carracks, gun ports, hatches opened in the hull of the ship, also became standard in shipbuilding. This allowed heavy cannons to be lowered from the deck to a position closer to the ship's center of gravity. As a result, ships became more stable, and the face of naval warfare changed completely. The carraca was not merely a cargo ship but also the first true symbol of power for global empires. While the carraca and caravels were discovering new worlds with the power of the wind in the oceans, a 1,000-year-old tradition was evolving and continuing in the inland waters of the Mediterranean, galleys. These ships, inherited from the triremes of antiquity, were the fundamental military units of maritime powers such as the Ottoman Empire, Venice, and Genoa throughout the Middle Ages and the Renaissance. The galley represented absolute freedom of movement provided by human power in enclosed seas where the wind was weak or changed direction. The design of a galley focused on speed and maneuverability. Its long, slender, low-slung hull made it as fast as an arrow. The main source of power on these ships was not the sails, but the rowers. With a system called zenzile, each bench could accommodate 3 or more rowers, and this enormous human power could propel the ship to high speeds even in the calmest weather. However, accommodating so many people in such a small space created significant logistical and hygiene challenges. Therefore, galleys usually sailed close to shore and frequently landed to replenish water supplies. In Ottoman naval architecture, galley construction was bound by engineering standards. The imperial arsenal in Istanbul was one of the world's largest and most organized production centers. Here, the skeleton of a galley was made of oak, and its outer planking was made of pine. The ram at the bow of the ship and the heavy cannons targeted enemy ships directly. In some of history's greatest battles, such as the Battle of Lepanto, hundreds of galleys faced each other, and the maneuverability of these ships determined the outcome of the battle. The galley's weakest point was stormy open seas. Due to their low freeboard, they risked sinking in large waves, and their cargo capacity was negligible. However, strategically, no wind-powered ship could match a galley in narrow straits and shallow coastal waters. These elegant but deadly machines, the true masters of the Mediterranean until the mid-17th century, went down in history as the ultimate example of the balance between human muscle power and water resistance in shipbuilding. Zenotation spot by the middle of the century, neither the cumbersome galleys nor the galleons confined to shallow waters could fully meet the needs of ocean empires. The Spanish developed a type of ship that was both large enough to carry enormous loads of gold and fast and armed enough to withstand pirate attacks. The galleon. Galleons were the result of a search for balance in naval architecture. The carracken's high and wind-catching bow, forecastle, was lowered and the hull length was extended. This structural change made the ship more stable against the wind and enabled it to travel much faster. These ships, which had 3 or 4 masts, used square sails as the main propulsion, while the latten sails on the rear masts maintained maneuverability. The greatest technical innovation in shipbuilding, however, was in hull strength. Galleons had specially designed double-plated hulls to carry heavy cannons. Cannons were now arranged not only on the upper deck but also on a special gun deck behind hatches opening onto the sides of the ship. This lowered the ship's center of gravity, increasing its stability and transforming the galleon into a floating fortress. A single galleon, with 40 to 60 cannons on its sides, had the power to destroy a city. Spanish galleons were the backbone of the legendary treasure fleets that carried silver and gold from America to Europe. However, these ships were not unique to Spain. The English refined the galleon design further, producing lower and faster models known as race-built galleons. Sailors like Sir Francis Drake achieved great successes against the Spanish Armada using these fast galleons. Galleon construction was a state project requiring the felling of thousands of oak trees, months of labor, and enormous budgets. The construction of a galleon symbolized the coordination capabilities of shipyards, considered the most technologically advanced factories of the time. Galleons ruled the seas for nearly 2 centuries as the most iconic silhouette of the sailing ship era and defined the boundaries of the colonial era. Zenotation spot at the beginning of the 17th century, in the midst of naval warfare, the Dutch adopted a completely different philosophy in shipbuilding: maximum profit, minimum cost. A concrete example of this philosophy was the flight type of ship, which changed the history of world trade. While galleons were designed for war, flights were produced solely for trade and were the first true cargo ships in history. The design of the flight ships was quite unusual. Their hulls were pear-shaped, that is, they were wide at the waterline and narrowed towards the deck. There was a very clever financial reason for this design. At that time, countries such as Denmark calculated the tax they levied on ships based on the width of the deck. By keeping the deck narrow, the Dutch saved on taxes while still being able to carry enormous amounts of cargo thanks to the wide hull below the waterline. Technical details in shipbuilding were also efficiency-focused. Flight ships could be managed with far fewer crew members than similarly sized vessels. Thanks to complex rope and pulley systems, dozens of sailors were not needed to manage the sails. This reduced operating costs and provided more space and budget for cargo. These ships, usually built from light but durable pine wood, rolled off the shipyards like they were coming off an assembly line, thanks to the Netherlands' mass production capabilities. Flight ships did not carry heavy weapons. For the Dutch, placing heavy cannons on a ship meant sacrificing valuable cargo space and making the ship heavier. Instead, these ships usually traveled in convoys or on safe routes. This strategy paid off, and the Dutch East India Company, VOC, quickly became the world's wealthiest commercial organization thanks to its fleets of flight ships. These ships could be seen everywhere, from Europe to Asia, from the Baltic Sea to America. The flight proved that shipbuilding was not just an engineering discipline but also an economic science. The Dutch's pragmatic approach made them the sea truckers of the 17th century and ushered in the golden age of global trade. Throughout history, shipbuilding was shaped not only by the efforts of individual craftsmen but also by the massive industrial complexes established by states. The first and most magnificent example of this development worldwide was the Venice Arsenal, the heart of the Venetian Republic. This was the largest industrial center of the Middle Ages, considered the forerunner of the modern factory and mass production. The Venice Arsenal carried out shipbuilding by dividing it into parts using an assembly line system. Behind the massive walls surrounding the city, thousands of workers, carpenters, caulkers, sailmakers, and foundry masters worked in perfect coordination. While the skeleton of a ship was being assembled in a dock, it was outfitted at other stations as it moved along the water. The Venetian arsenal was so advanced that it is said they could produce a fully equipped galley per day in emergencies, such as preparing for war. This industrial revolution in shipbuilding also brought standardization. Every part was now produced in predetermined sizes to fit every ship. This incredibly accelerated repair and maintenance processes. The massive rope factory, Corderia, within the arsenal produced the highest quality and longest ship ropes in all of Europe. These hemp ropes were vital elements that determined a ship's resistance to wind. At the same time, timber management was also a critical part of this process. The Venetians selected oak trees that grew naturally curved for ship ribs, even planning forests according to this need. This living shipyard logic maximized the structural integrity of the ships. Venice's absolute commercial success at sea was based not only on the courage of its sailors but also on this tremendous engineering and logistical organization. The system established by the arsenal later became a model for all European states. Every major power, from England to the Ottomans, established their own central shipyards, transforming shipbuilding from a craft into a strategic industry. Shipbuilding was no longer just about making a boat. It meant managing the most complex technological systems that reflected a state's power. The Ottoman Empire kept the galley type, the vessel best suited to the geographical structure of the Mediterranean, at the center of shipbuilding for centuries. The imperial dockyard in Istanbul had one of the world's largest production capacities and was a massive factory employing thousands of workers. However, towards the end of the 17th century, with the arrival of giant ocean-going galleons in the Mediterranean, Ottoman engineering underwent a major transformation. This transition in Ottoman shipbuilding was not merely a design change, but also a logistical and strategic revolution. While galleys relied on or power, galleons were massive structures powered entirely by wind and capable of carrying much heavier cannons. Ottoman chief architects and engineers studied European designs and developed their own unique galleon style. Ottoman galleons were generally built wider and more balanced than their Western counterparts. The choice of materials used in shipbuilding during this period was of vital importance. The empire used oak and pine timber from the Black Sea coast and the forests of the Balkans. Approximately 2,000 to 3,000 mature trees were needed to build a galleon. The timber was soaked in special pools to increase its resistance to seawater and fungi, then watertightness was ensured by applying tow and pitch between the planks in a process called caulking. Under the leadership of visionary sailors such as Mezamorda Hussein Pasha, shipbuilding was standardized with the Bari Canonomachy, naval code, published in 1682. The size of the ships, the number of cannons they could carry, and their crew capacity were determined according to mathematical rules. The three-masted galleons built during this period could carry over 100 cannons and re-establish the Ottoman Empire's deterrent power at sea. Ottoman engineers, striving to combine the maneuverability derived from the Kadurga tradition with the firepower of the galleon, produced original solutions in shipbuilding. For example, the carvings and decorations on the bows of the ships were not only aesthetic but also symbols representing the grandeur of the empire. Ottoman shipyards took their place in history as the most important centers reflecting the synthesis of Eastern and Western wood shipbuilding arts. Xenotation spot by the 19th century, naval warfare had evolved from duels between individual ships into a chess game played by massive floating fortresses. The most powerful symbol of this era was the ships of the line, named for the strategy of forming a line, during battle and firing all the cannons on their sides simultaneously. These ships represented the most complex and deadly point reached by the art of wooden shipbuilding. Building a ship of the line was the most expensive and challenging technological investment a state could make. They were generally divided into three main categories. First-rate ships of the line had at least 3 decks and carried more than 100 heavy guns. Approximately 3,500 oak trees, aged 60 to 100 years, were used just to construct the skeleton of these giants. The famous British HMS Victory is the most distinguished example of this engineering marvel that has survived to the present day. Shipbuilders revolutionized hull design to keep this immense weight balanced on the water. The lower part of the ship was covered with 2 or sometimes 3 layers of thick wood to make it resistant to cannonballs and rocks. The gun decks were built very close to the waterline so as not to upset the ship's balance, which made it impossible to use the guns on the lower decks in stormy weather. Navigation and equipment also reached their peak during this period. Thousands of meters of hemp rope were combined with a complex pulley system to control the enormous sails. The ship's main mast could rise up to 60 meters into the sky. To prevent the wood from rotting, ship hulls began to be covered with copper plates. This process not only protected against woodworm but also increased speed by reducing friction. A sailing ship was a self-sufficient microcosm, capable of accommodating over 800 people. These vessels were the absolute rulers of an age dominated by wood and gunpowder, carrying the power of empires to the remotest corners of the ocean. The meticulousness and enormous cost of their construction clearly demonstrated why dominion over the seas was reserved solely for the world's wealthiest and most organized states. As shipbuilding reached enormous proportions, sailors' greatest enemy was not storms, but not knowing where they were. For thousands of years, sailors could measure latitude, north-south position, by observing the sun and stars. However, calculating longitude, east-west position, was impossible. A single miscalculation could cause a massive galleon to crash unexpectedly into rocks and break apart. Xenotation spot in the 18th century, this problem turned into an engineering crisis that directly affected shipbuilding and maritime safety. The solution lay not in the sky, but in the gears inside a small box. English carpenter and clockmaker John Harrison succeeded in producing a clock that was unaffected by sea motion, humidity, and temperature changes, the marine chronometer. This invention even changed the interior design of ships. Special compartments and suspension systems, roll-resistant beds, were designed on ships to keep the precise chronometers stable. A sailor could determine his exact position on Earth by comparing the time at the port of departure with the sundial at his current location. This meant that ships could now safely use the most direct routes across the ocean without having to follow the coastline. This precision in navigation increased the demand for speed in shipbuilding. A captain who knew his exact position did not hesitate to steer his ship into the corridors where the wind blew hardest. This led to ship hulls becoming more aerodynamic and sail areas becoming even larger. Alongside the chronometer, the refinement of the sextant enabled sailors to measure the angle of celestial bodies in seconds. Maritime travel was no longer a game of guesswork but a matter of mathematical precision. This marriage of science and woodworking marked the end of the age of discovery while laying the foundation for modern maritime trade and global transportation. If battleships were the heavyweight boxers of the seas, frigates were undoubtedly the most agile and dangerous fighters in the middleweight division. At the beginning of the 18th and 19th centuries, frigates represented the ideal balance between speed and firepower in shipbuilding. These ships, usually equipped with a single main gun deck, were the eyes and ears of the seas, capable of operating independently of the fleet, conducting reconnaissance and protecting trade routes, unlike ships of the line. From a naval engineering perspective, the design of frigates was based on minimizing water resistance. Their hulls were much longer and more slender than those of line-of-battle ships. This structure gave them incredible speed and allowed them to sail at sharper angles against the wind. One of the most famous frigates of the period, the American USS Constitution, Old Ironsides, was renowned for the live oak used in its hull construction, which caused cannonballs to ricochet off its hull. The woodworking technology used in the construction of these ships was highly advanced. The internal skeleton was reinforced with complex crossbeams to withstand the torsional stresses generated when the ship maneuvered at high speeds. The rigging consisted of 3 fully equipped masts. This gave the captain the ability to move the ship even in the slightest breeze. Frigates are also heroes of maritime literature. They could cross oceans alone, chase pirates, or carry out secret diplomatic missions. Although their construction required less wood than line-of-battle ships, the quality of the materials used and the precision of the workmanship were much higher. This was because a frigate's only defense was often its ability to outrun its enemy or quickly surround it. Xenotation spot until the middle of the century, frigates remained an indispensable part of naval strategy. These elegant ships were the aesthetic and functional pinnacle of the wooden sailing age. They were the greatest proof that maritime transport was not just about carrying heavy loads, but also a modern operation based on speed and strategic flexibility. Xenotation spot by the mid-19th century, steam engines were slowly beginning to appear on the horizon, but sail technology had not yet had its final say. For industries where speed was paramount, such as the tea and gold trades, shipbuilders designed legendary ships called clippers that raced the wind. These ships were the last great masterpieces of the wooden sailing age, breaking speed records. The most distinctive feature that set clipper ships apart from others was their razor-sharp prows. While traditional ships pushed through the water, clippers sliced through it like a knife. Their hulls were unusually long and slender, minimizing water resistance. These three-masted giants had enormous sail areas that reached up to the sky. In fact, sometimes the total sail area reached thousands of square meters, and the ships seemed to fly over the water with the power of the wind. The materials used in shipbuilding had also evolved. Many clippers were built using the composite construction method, that is, the internal skeleton was made of iron, while the outer plating consisted of durable wood such as teak or oak. This method gave the ship both the strength of iron and the flexibility of wood. Famous clipper ships like the Cutty Sark crossed the oceans in less than 100 days to bring the freshest tea from China to England. However, this speed came at a cost. Clippers could not carry much cargo. Most of their interior space was limited due to their aerodynamic structure. Furthermore, managing such large sails required an extremely skilled and courageous crew. To prevent the massive masts from breaking in stormy weather, shipbuilders began reinforcing the rope and pulley systems with the most modern steel cables. The clipper era was brief but glorious. With the opening of the Suez Canal and the increase in coal supply points for steamships, these last representatives of sail gradually retired. However, clipper ships went down in history as the most aesthetic proof of how far humanity could push nature's limits using only wind and wood. Xenotation spot at the beginning of the century, the age-old tradition of sailing faced a disruptive challenge: James Watt steam engine. Ships no longer had to look to the sky and wait for the wind. The power of coal and fire opened the door to a new era in maritime transportation. However, the first steamships bore little resemblance to the propeller-driven giants we know today. One of the first successful attempts, Robert Fulton's Clermont ship, moved thanks to enormous paddle wheels placed on its sides. This necessitated a major structural change in shipbuilding. Wooden hulls had to carry heavy steam boilers and tons of coal, as well as withstand the violent vibrations created by the engine. This led to ship frames being reinforced with much thicker beams and the central weight balance being recalculated. Wheel-driven ships were marvels on rivers and calm inland seas because they could move steadily even against the current. However, there was a problem on the open ocean. When the ship pitched between waves, one wheel would rise completely out of the water while the other would be submerged. This caused energy loss and made the ship shake. Ship engineers initially tried a hybrid method to solve this problem. Ships had both massive masts and steam engines at the same time. The introduction of the steam engine transformed shipyards into machine factories. Now, iron workers and mechanical engineers joined the carpenters. Steam-powered paddle-wheel ships accelerated transportation, particularly on the Mississippi River in America and the English Channel between England and France, changing the face of trade. However, steam's real triumph at sea would come when paddle wheels were replaced by propellers. Although paddle wheel ships were successful on rivers, a more efficient system was needed to cope with the rough waves of the ocean. In the 1830s, engineers realized that a screw, propeller, rotating underwater could propel a ship much more powerfully. The biggest breakthrough in this field came with the SS Great Britain, designed by the legendary engineer Isambard Kingdom Brunel. Launched in 1843, this ship achieved three major revolutions in shipbuilding at once. Xenotation spot iron hull. Ships were no longer made of wood but of massive iron plates riveted together. This allowed ships to be much larger and stronger. Xenotation spot propeller system. The cumbersome side wheels were gone, replaced by a massive six-bladed propeller mounted at the stern. Xenotation spot massive size. It was the largest ship in the world at the time and set the standard for transoceanic passenger transport. The introduction of the propeller radically changed ship architecture. The engine and boiler room were now placed in the lowest and central part of the ship, lowering the center of gravity and increasing stability. Special watertight tunnels called shaft tubes were developed to allow the propeller shaft, the long arm connecting the engine to the propeller, to pass through the hull. Propeller technology combined the maneuverability of sailing ships with the unstoppable power of steam. Initially, sailors approached the propeller with suspicion. The British Royal Navy even organized a tug-of-war by pulling a paddle-wheel ship and a propeller-driven ship in opposite directions. The propeller-driven ship proved its superiority by dragging the paddle-wheel ship. This victory marked the official end of the age of wooden sails and the beginning of the modern era of seafaring, ruled by steel and propellers. The combination of propeller and iron hull completely changed not only trade but also the nature of naval warfare. During the Crimean War, it became clear how vulnerable wooden ships were to the new generation of explosive shells. The destruction of a massive frigate with a single hit made the concept of armor in shipbuilding imperative. The first and most formidable representative of this new era was the British ship HMS Warrior. Launched in 1860, HMS Warrior was history's first true ironclad. Shipbuilding engineers placed 11-centimeter thick iron plates over the wooden hull to protect the waterline and vital sections. Behind this iron armor was a 45-centimeter thick layer of teak wood. This structure formed an impenetrable shield, even against the heaviest cannons of the era. The construction of these ships brought new challenges in engineering. Xenotation spot weight management. Thousands of tons of armor plating could sink the ship. Therefore, ship hulls began to be built much wider and deeper. Xenotation spot corrosion control. Contact between iron and steel and seawater caused rusting. Shipbuilders developed chemical paints and special coating techniques to protect the hull. Xenotation spot engine power. Larger and more efficient steam engines were designed to move the enormous weight of the armor. HMS Warrior was so powerful that no enemy ship dared to approach it. However, technology was advancing so rapidly that within just 10 years, even this massive ship was considered obsolete. This was because modern warships, which completely abandoned wood, had rotating turrets, and were built entirely of steel, were now entering the scene. This process marked the final point where shipbuilding ceased to be a craft and became part of heavy industry and metallurgy. Xenotation spot at the very beginning of the century, in 1906, the HMS Dreadnought, launched in England, rendered all previous ship designs obsolete in a single day. This ship was so revolutionary that all warships built after it were called dreadnoughts, while those built before it were called pre-dreadnoughts. From a naval engineering perspective, the dreadnought introduced two major innovations. Xenotation spot all big gun. While older ships carried many guns of different sizes, this ship was equipped with massive guns of the same size and with a very long range. This enabled the ship to destroy the enemy from a great distance. Xenotation spot steam turbines. Steam turbines were used for the first time instead of traditional piston engines. This technology made the ship much faster, smoother, and more reliable. The construction of these massive steel fortresses ushered in a new era in metallurgy. Ships were no longer made of just iron, but of specially hardened nickel-steel alloys. Shipbuilders reached the pinnacle of riveting technology, millions of steel rivets were hammered into the hull using massive presses, creating a watertight and unshakable hull. In addition, the ship's interior design was based on a compartmentalization system. The ship was divided into thousands of small watertight compartments so that it would not sink even if it took a hit underwater. Building ships during this period was no longer just shipbuilding, but a massive national project carried out with the coordination of thousands of engineers, mathematicians, and metalworkers. With the launch of the dreadnought, maritime transport and defense completely evolved from the romanticism of wood to the cold, calculated power of steel. Xenotation spot the beginning of the century was an era of splendor not only for warships but also for civilian shipping. Millions of people emigrating from Europe to America and wealthy individuals who wanted to turn this journey into a luxury spectacle initiated the transatlantic, ocean liner era in shipbuilding. These ships became the largest man-made moving structures. The most iconic representatives of this era, the Olympic, Titanic, and Mauretania, pushed the boundaries of ship engineering. The technical innovations used in their construction included xenotation spot double-hulled hull. A double-layered steel hull was designed to enhance the ship's safety. Xenotation spot electrical revolution. A massive electrical network was installed throughout the ship to power thousands of lights, elevators, and kitchen equipment. Xenotation spot luxury and weight balance. The enormous ballrooms, marble staircases, and pools on the upper decks raised the ship's center of gravity. To prevent this massive structure from rolling at sea, engineers placed thousands of tons of ballast in the lower sections of the ship. However, the Titanic disaster in 1912 painfully taught that safety in shipbuilding is more important than design. After this event, shipbuilding regulations, SALAS, International Convention for the Safety of Life at Sea, changed completely. Now every ship had to have enough lifeboats to accommodate everyone on board, and radio rooms had to be kept open 24 hours a day. Additionally, the height of watertight bulkheads was increased to prevent ships from sinking in situations such as collisions or encounters with icebergs. Engineers began designing watertight ceilings to prevent water from flowing from one compartment to another. These massive ships became the ancestors of modern cruise ships and transformed maritime transport from a mere journey into a way of life. After World War I, naval strategies changed radically. It was no longer enough to have the biggest guns. It was necessary to see beyond the horizon and be able to attack there. This need gave rise to one of the most complex engineering projects ever undertaken in shipbuilding, the aircraft carrier. Building an aircraft carrier meant designing a floating airport. Ship engineers had to find solutions to unprecedented problems to bring this massive structure to life. Xenotation spot flight deck and stability. The ship needed a flat, wide runway at the top. However, placing such a wide and heavy structure at the top could destabilize the ship. To solve this, the lower hull was made much wider, and the engines and fuel tanks were placed in the lowest compartments to maintain balance. Xenotation spot island structure. The control tower, island, was shifted to the ship's starboard side so as not to interfere with flight operations. This resulted in the ship having an asymmetrical weight, and engineers used fuel and water tanks on the other side of the ship as counterweights to compensate for this imbalance. Xenotation spot stopping and launching systems. Steel cable arresting systems were developed to enable aircraft to stop within a very short distance, while steam catapults, later developed, were used to launch them. With World War II, aircraft carriers replaced battleships as the new rulers of the seas. These ships were not only weapons of war, but also floating cities and massive fuel depots. Transporting thousands of tons of aviation fuel and ammunition required the highest level of fire and explosion safety on board. Thus, fire barriers and advanced ventilation systems became standard features in ship construction. While shipbuilding reached enormous proportions on the surface, a completely different technology was emerging beneath the water. Submarines had to contend with hydrostatic pressure and life support systems, the most challenging disciplines of naval engineering. Building a submarine is essentially designing a watertight pressure tube. The fundamental revolutions in shipbuilding were as follows. Xenotation spot double hull design. Modern submarines consist of two nested hulls. The inner pressure hull protects the crew from the immense water pressure at depth. The outer hull provides a hydrodynamic form for faster movement through the water. The spaces between these two hulls are ballast tanks, which enable diving and surfacing. Xenotation spot diving principle. Naval architects used Archimedes' principle in a controlled manner. When water fills the ballast tanks, the submarine becomes heavier and dives. When pressurized air is pumped into the tanks to expel water, the submarine becomes lighter and surfaces. Xenotation spot propulsion systems. Initially, diesel engines operated on the surface, while batteries were used underwater. However, with the nuclear energy revolution in the 1950s, submarines gained the capacity to remain underwater for years without refueling. Submarine construction pioneered watertight technology. Huge steel plates must be welded with millimeter precision to withstand the pressure hundreds of meters below the surface. Furthermore, the development of sonar technology for underwater navigation also necessitated the calculation of sound wave movement in water during shipbuilding. Submarines are proof that shipbuilding is not just a battle on the surface, but also a silent and dangerous engineering battle in the depths. Until the 1950s, loading ships was a nightmare. Thousands of sacks, crates, and barrels were placed into the ship's holds one by port workers using cranes. This process took days, sometimes weeks. However, in 1956, American trucking entrepreneur Malcolm McLean brought to life a simple but ingenious idea that would fundamentally change shipbuilding and the global economy: the container. With the advent of the container, ship architecture had to change completely. Instead of multiple compartments inside the holds, huge, deep spaces were now needed. These new generation ships were called container ships, cellular container ships. The fundamental changes in shipbuilding were as follows. Xenotation spot cell guides, vertical rails, guides, were installed in the ship's holds to ensure that containers fit perfectly on top of each other. This allowed containers to be stacked with millimeter precision, like Lego pieces. Xenotation spot deck strength. Containers were stacked not only in the holds but also on the deck, reaching heights of 10 to 15 layers. To carry this enormous weight and maintain the ship's stability, the hulls were built much wider and with heavier bases. Xenotation spot torsional resistance. Since the upper part of container ships is completely open due to the hold covers, there is a risk of the hull twisting in rough seas. To prevent this, engineers added massive steel box girders to the sides of the ship. Today, a container ship can carry more than 24,000 containers in a single voyage. If these loads were loaded onto trucks, it would form a convoy over 100 kilometers long. This increase in efficiency in shipbuilding has reduced transportation costs so much that today, a product manufactured on the other side of the world can be delivered to your doorstep for less than it would cost to transport it locally. Container ships are the true architects of modern globalization. Our shipbuilding journey has progressed from wooden hulls to the cold strength of steel, and from there to the pinnacle of digitalization and environmental awareness. Today, shipyards are no longer just places where metal is shaped. They are high-tech centers where artificial intelligence, robotic arms, and sustainable energy systems are integrated. The latest major transformations in modern shipbuilding are as follows. Xenotation spot liquefied natural gas, LNG, and hydrogen. To reduce their carbon footprint, ships are now designed to run on clean energy sources such as LNG or hydrogen instead of heavy fuels. This necessitates the construction of massive, high-pressure, cryogenic, extremely cold, storage tanks inside the ship. Xenotation spot autonomous voyages, ships with no one in the captain's cabin, managed entirely by sensors and artificial intelligence, are no longer a fantasy. Autonomous cargo ships launched in countries like Norway can detect obstacles at sea faster than the human eye using radar and LiDAR systems. Xenotation spot modular construction. Ships are no longer launched in one piece. Huge sections, blocks, of the ship are built in different areas of the shipyard, fitted with internal systems, and then assembled like a jigsaw puzzle using giant cranes. This method reduces the construction time of a massive passenger ship from years to months. Shipbuilding is the most tangible story of humanity's effort to understand and manage nature. The curiosity of humans who carved a log and launched it into the water thousands of years ago is the same as the passion of engineers who designed ships that plan to go to the stars today. The seas are still the world's largest highways, and ships continue to be the most faithful carriers on these highways.